Think about a software engineer who released a social media application. At the first week of usage, there are 500 users in the application. At the second week of usage, the number of users has grown to 3,000 users. At the third week of usage, we now have 25,000 users in the application. At the fourth week of usage, we now have 120,000 users in the application. At this stage, things began to get critical. The application began to freeze, and to make it worse, it crashed. In this type of situation, this is where big O notation comes to play. Getting your code to work is the first step, but what happens when your data set begin to grow? Now, what is big O notation? Big O notation is a general concept in computer science that enables programmers to measure how complex an algorithm or block of code is in terms of both time and space. Big O notation, which is the N, indicates the input size, while the O is the worst case scenario growth rate function. You can write a code that works without knowing big O, but it is important you know the performance of your code. It is paramount you know how to measure algorithm performance. Big O notation can express the best, worst, and average case running time of an algorithm. It is important we know that big O metrics does not take certain things into consideration, such as the processor of your computer, the RAM, the programming language, or the runtime environment. This is important. What Big O does is to estimate the worst case scenario of a block of code. Big O notation is divided into two parts. We have the time complexity and the space complexity. However, more preferences is given to the time complexity because we can run out of space, then we can pad up the space. We can add more space if there is no space. But however, when it comes to time, we can add more time. We can pad up time. So what is time complexity? Time complexity is a type of estimation complexity that describes the time required to execute an algorithm. Time complexity measures how long it takes to execute in terms of computational steps, while space complexity refers to the total amount of memory space used by an algorithm or a program, including space of input values for execution. The space complexity of a function measures the amount of memory your code uses. Simple put is time complexity is the time it takes, is the estimated time it takes for a block of code to run, while the space complexity is the amount of space used while a program is run. The following are the big O notation metrics. There are a lot of mathematical expression which has been done under the hood to get to these metrics. However, if you are working with big O notation, this is what you are going to use to measure the performance of your algorithm. The first one is O of 1, which is the constant time. And what this means is at worst case, an algorithm that is labeled O of 1 will not exceed O of 1. We have the next one, which is the O log n. This is logarithmic time complexity. And we have the next one, which is O of n, which is the linear time complexity. The next one is big O of n log n. This is log linear time complexity. and we have the big O of n raised to power 2, which is the quadratic time complexity. And we have the big O of n raised to power 3, which is the cubic time complexity. And we have the O2 raised to power n, which is the exponential time complexity. Lastly, we have the On factorial, which is the factorial time complexity. This list is arranged from the best performance to the horrible performance. So I want you to take note of it. From O of 1 down, these are the best performance to the what? The horrible performance. To see this for more clarity, we can visit the big O cheat sheet. So let us look at this. Now, if you look at this part at the bottom, you will notice we have the green part, right? We have O of 1, which is the constant time, right? And we also have the O log n. So you can see the green part, right, is excellent. Whatever algorithm that is within this big O notation is excellent. You can see it doesn't rise with time. Especially the O of 1, it moves in a constant time. Then followed by the O log n. You can see it also good, right? It marks as good. So any algorithm within this part is marked as what? Good. Then we have the O of n, which is the linear time, right? So this part is fair. You can see this part what is fair. So you can see the next one we have here is On log n. At this stage, it's actually bad. You can see it bad, but it's fairly acceptable. We can manage it. So your algorithm should not take much data. Anything above this part, if you write an algorithm that gets to this part, this is horrible, right? And this is not a good operation. This can crash your system. Any algorithm at On raised to power 2 or On2 raised to power n or n factorial is very dangerous for your system. If you write an algorithm like this, only if you want to make use of it with a tiny data set. Else, anything above that is going to crash your system. So the next thing we want to do is to explore these metrics one after the other in details. So thank you very much for watching. I will see you in the next video.